Hello children, welcome to Advanced Level Physics. Today we will be talking about Unit 6, Electrostatic Force Fields. Before I commence with the unit, let's talk about the background that you have already learned which associates with the unit. By now you have already learned the concept of a field, and under the concept of a field you have discussed that there are types of force fields and which are vector fields. One type of force field you all have discussed by now, the gravitational force fields, and the second type of force field that we will talk about, a vector field, is an electrostatic force field. So we have to know first how that there are 4 competency levels in the topic, and that we will be talking about 6.1, the first competency level, where we will be talking about the associated laws associated to electrostatic forces and the distribution and magnitude of electrostatic fields produced by different charges. Let's first talk about how an electric field is created and what an electric field is. We say an electric field is a physical field that surrounds a charge, and as a result, when you keep another charge near the first, it is either attracted or repelled from the first. We say that an electric field can be created either by a charge, electric charge, or a time varying magnetic field. Let's take a simple example that you are all familiar with. Say you use a plastic comb, you comb your hair, and then if you bring the plastic comb close to small pieces of shredded paper, we know that the small pieces of paper attract to the comb. Or even if you bring the comb close to your hand, we feel that the hair rises in the hand because of the electrostatic field. Now, a couple of terms that we used already is an electric charge. We know that, but let's go through that again. We say an electric charge is a fundamental property of matter that causes an electric field when you keep it in an electromagnetic field. We know that the mass is also a fundamental property of matter, and when you keep the mass in a gravitational field, it experiences a gravitational force. Similarly, the electric charge is that fundamental property of matter which is able to exert a force, an electric force on the charge or on the matter when it's kept in an electromagnetic field. Now, we know that there are 2 types of electric charges, positive charges, negative charges. We say positives are carried by protons and negatives carried by electrons. And if you think of the facts that you already know, we know that like charges, for example, positive charges, proton, negative charges, electrons, we know that like charges repel each other, and unlike charges, opposite charges attract each other. Well, if you discuss the background a little bit, we say if you take matter, it's made of atoms. Every atom has a nucleus. Around it, there are covalent electrons circulating. We say the atom contains the protons, positive charges, and around the atom, around the nucleus, where the protons exist, covalent electrons circulate. So we say if you take an atom, matter, it will originally be a neutral one because equal number of protons and electrons, they both contain equal amount of charges. As you know, charge has an SI unit of coulomb. So protons have a positive 1.6 into 10 to the power minus 19 coulombs, and electrons have a negative 1.6 into 10 to the power minus 19 coulombs, and in any object we say equal number of protons and electrons make the body a neutral body. Now, if we want to create an electric field, we have to give the body a charge. Now, how do we do this? We say we have to electrically charge the body. We say either give the body more electrons or give the body more protons. Now, as you all know, the protons exist in the nucleus. So, obviously, the protons can't flow. We say that when an excess of electrons appear, that the body will be negatively charged, and if you remove the electrons from a neutral body, an excess of positive charges appear in the nucleus, will have a positively charged body. So, it is a matter of either giving more electrons to the body or removing the electrons from the body that we can electrically charge it. Now, if you look at the ways that we can charge an object, we mainly discuss about 3 ways. One way is to charge by friction. When you talk of charging a body by friction, there we take 2 material of different types of material and you rub against each other. What you do is you are stimulating the bodies, the electrons, and you are transferring from one body to the other, you are transferring negative charges which are movable electrons. For example, if you take a glass rod and you rub it with a piece of silk, what happened? Originally, both bodies, the glass rod and the piece of silk, are originally neutral bodies. Equal number of protons, electrons are there. But when you rub against each other, what happened is that from the glass rod, electrons flow into the silk, and as a result, the silk is left with an excess of negative charges, electrons, and the glass have a lack of negative charges. So, an excess of positive charges, we say glass rod is positively charged, silk is negatively charged. And a similar example is where we rub ebonite with a piece of woolen cloth, where then what happened? Originally, both ebonite and the piece of woolen are neutral bodies, but when they rub against each other, electrons in the woolen cloth gets transferred to the ebonite rod, which gives an excessive negative charge to the ebonite rod. So, it is a negatively charged body. The woolen cloth have a lack of electrons now. So, it is similar to an excessively charged positive body. So, that is the first method of charging. This is by rubbing, this is by using friction. Now, if you think of the second method, we say charging by conduction. Now, in order to carry out such a process, we are using one charged body and we are using the charged body to give the charge to the second body, which is an uncharged body. Now, in this method, what we do is we bring the two bodies to touch each other. Let us take an example. For instance, I have a glass rod which is rubbed with a silk. So, now it is a positively charged glass rod, and that is a metal object which is initially neutral. But we know what is a metal object? Metals have excessive large number of carriers. What are carriers? We call them free electrons that can freely move about. And it is mounted on an insulating rod. So, if we give it the charge, insulating rod that blocks the channel from charges flowing from this to the surface. So, what happened? The charges can will be sustained in the metal object. Now, what happened? When you bring the glass rod which is already charged, we bring it to contact the metal object. What happened? We say the positive charges in the glass rod transfer to the metal object. Really what happened? Positive charges can't flow, as we know. What happened? Electrons will flow into the glass rod, and as a result this will have lack of electrons, so more positive charges, which we say is similar to transferring positive charges from the glass rod to the metal object. So, what we did was we made them contact, and as a result the same charge that was in the glass rod was transferred to the metal object. So, by contact, by conduction, we are able to transfer the same charge on the glass into the metal object. If we think of the third method of giving a body a charge, this is by charging a body by induction. Here also we are using a charged body to give the charge to an uncharged body, but this time it is without touching. So, how we are going to do this? We said we will take the same example we did earlier. So, I am using the same glass rod charged, stored with a positive charge, for example glass rubbed with silk, and I am bringing it close to this metal sphere mounted on an insulating support. So, when I bring the positively charged glass rod near the metal sphere is initially a neutral body having equal number of positive negative charges. In the presence of the positive charge, the metal sphere's negative charges attract towards that side of the sphere, while the same charge, like charge plus positive charge, is repelled to the other side of the sphere. So opposite charges are attracted, like charges are repelled. Now while having the glass rod being present there, if you now earth the metal sphere, that is a channel is introduced here, a good conducting metal, or you can simply touch it. When you touch it and earth it, what happened? These positive charges will further try to repel from it. So as a result, the positive charges will flow into the ground. In other words, negatives will neutralize it. So in the presence of the positive charges, and negative charges will be stored. If you now remove the positively charged glass rod, there still is a negative charge sustained in the metal sphere. It was initially a neutral body, but now negatively charged. You see, in the previous example, I used the same glass rod, but there I contacted the glass rod into the metal and transferred the same positive charge into the metal sphere. But this time, I did not bring them to contact. Instead, I transferred the opposite type of charge into the body without contacting it, which is called the method of induction. If I take further on, if I move on to another step, now I am using the same glass rod, slight difference. Earlier I used only one metal sphere, this time I am using two metal spheres. So before I bring it, I bring the two metal spheres to contact. And now when I bring the same positively charged body, what happened? All the negative charges in the neutral system, in the neutral two spheres, all negative charges will be attracted, positives will be repelled. So earlier this body was neutral, but now it contained an excessive negative charge. Earlier this was neutral, now it contained an excessive positive charge. And if I separate them now, this sustain a negative, this sustain a positive, and if I remove the glass rod, if the two spheres are close to each other, the negative and positives will attract, but they cannot neutralize each other because there is an insulation in between. The negative will sustain, a positive will sustain, and if you separate it, the charges will get distributed uniformly all over the spheres. So we learned three methods to give a body a charge. Now if we further move on, we say in the previous parts we discussed, we saw whenever a positive positive, a negative negative, or a positive and a negative are brought near each other, that they either attract or repel from each other. Now in gravitational fields you all learned, if there were two masses, one mass is kept in the field of the other, thus there is a mutual attractive force between them introduced by Newton's universal law of gravitation. In this, a similar law is introduced to discuss about this mutual attractive force, and this mutual attractive force, either repulsive or attractive, are also called electrostatic forces or Coulomb forces. So if you come to Coulomb's law, it explains, the law describes the magnitude of the mutual force that exert between 2 point charges kept apart from each other. The law says that if you take 2 point charges, separated by a certain distance from each other, that the 2 point charges can either attract. If they are both like charges, they may repel from each other. If the 2 point charges are opposite charges, they will be attracted towards each other. So the Coulomb's law states that the magnitude of the mutual force, it's a mutual force. So we know force comes in a pair. So the two forces are equal but in opposite directions. That the mutual force, the magnitude of the mutual force, this force is directly proportional to the magnitude, product of the magnitude of the two charges, and is inversely proportional to the square of the separation between them. So the two forces, magnitude of the forces is directly proportional to the product of the magnitude of the two charges, and is inversely proportional to the square of the separation between them. So, inversely proportional to square gives the name Coulomb's inverse square law. Now, if I introduce the proportionality constant to this is what we get. So, by the Coulomb's law, we are introducing the two forces F1, F2 forces which are equal to each other. It's a mutual force, and the proportionality constant is Ke. The proportionality constant is called Coulomb's constant, and for convenience a value is given to you where the Coulomb's constant can be expressed as a 1 upon 4 pi epsilon naught, where epsilon represents the permittivity of the medium, which is a factor that expresses the transmission of electric field. So, permittivity of the medium, and if it's epsilon naught, it is referred to as the permittivity, electric permittivity in free space, vacuum, free space, air, all treated the same way. So, epsilon naught refers to the permittivity, electric permittivity of a free space, also called as vacuum electric permittivity. And for all other media apart from free space or air, it is always denoted by a constant, a value referred to as relative permittivity or dielectric constant, where epsilon r can be used. Say for example, epsilon r for a particular medium is 1.5. We say the permittivity or the absolute permittivity of that medium is 1.5 times the permittivity of free space. I will repeat, the absolute permittivity of that medium is 1.5 times the vacuum permittivity, vacuum electric permittivity of the medium. So, we say permittivity is the property that depends on the medium. If we think of the SI unit of Coulomb's constant, you know the force is measured in newtons, SI unit. The SI unit of charge are coulombs, and the SI unit of distance, separation, is meter. So, by that we can come to the SI unit of Coulomb's constant as Newton meter squared per Coulomb squared, and from that we can come to the SI unit of permittivity given by Coulomb squared per Newton per meter squared, also expressed as farads per meter. According to Coulomb's law, I am talking about Newton's law also here, mutual force. We know according to Newton's third law, the forces are equal in magnitude and opposite in direction. So, it is a mutual force, so the two forces are equal. So, when we express the Coulomb's law, if we express it in a mathematical form, we can express the Coulomb's force, mutual attractive force, by the equation Fe equals 1 upon 4 pi epsilon Q1 Q2 upon r squared, which is the mutual force between 2 point charges Q1 and Q2 kept in a medium with a separation of r between them. If we now try to observe how this force, the Coulomb force, vary with the distance between the same two charges, how it vary with the distance, we are trying to express it in a graphical form. Well, we know that by Coulomb's law that the force Fe is inversely proportional to the separation, square of the separation between them. So, if I try to explain this a little bit more, when r become very small, tends to 0, if you put 0 here, we know the value of the force, it tends to infinity. Similarly, if I consider that distance is increasing to a maximum, it become infinite, we know the force now become, when this distance is very large, we know the force tends to a minimum. So, force tends to 0. So, we say from the shortest distance between them to the greatest, when you move, when the charges are separated, the force vary from infinity to 0, and so we come to the curve that is expressed here. If you now look at the two figures, it is clear that when the distance is smallest, if you look at the two charges here, when this q is brought near, r is small, in that case the force tends to infinity, and when R increases, you move that charge away from it, R increases. We see that when R increases, the force tends to 0. So, it is clear that the variation between Coulomb force and the separation between the charges is something of this nature. Now, why do we have two graphs, positive and negative? Let me explain it this way. Now, if you keep the charge on that side, for the scale variation to the positive, we see the force exerted on this charge is towards the right. But if you bring that charge onto this side to the left of the source charge, what happened? We are moving it towards the negative side of the scale. When the distance increases towards the negative side, we see the force is towards the left. So, it indicates that the direction of the force has inverted. So, for the positive side of the scale, I drew the force to the positive side, and to the negative side of the scale, I drew the force to the negative side to indicate the vector property of the force. If you further move on to a question to implement, to apply to the Coulomb's law, let's try this. There are two electrons of mass 9.1 into 10 to the power minus 31 kilograms and charge 1.6 into 10 to the power minus 19 coulombs of each are placed at rest apart by 1 nanometer in free space. Compare the electrostatic force and the gravitational force between them. That is a part that you have already learned. So, let me draw the diagram for you. So, what we have are two electrons. Because of the two masses of the two electrons, they experience a mutual attractive force explained by Newton's universal law of gravitation. Let us use Coulomb's mathematical expression given by 1 upon 4 pi epsilon Q1 Q2 upon R squared. Well, in the question it says the two electrons are kept in free space. So, I have used epsilon naught here, and when I am replacing that value, the 9 into 10 to the power 9, which is introduced to you earlier, and the two charges are both electrons. So, I substituted the charges of the two electrons, and R, it says apart by 1 nanometer. So, 1 nanometer, I have to write this in SI units, that is going to be 10 to the power minus 9 meter. So, if I put that value there, R would be 1 into 10 to the power minus 9 square of it, gives me the electrostatic force exerted between, the mutual force between the two particles. If I now come to the gravitational force mathematical expression is given by G m1 m2 upon R squared, and if I substitute to that now, capital G, universal gravitational constant, we know that value, m1 m2, mass of both are electrons, same mass of the electrons, and the separation is once again 1 nanometer. I replace it there. So, when I solve them, if I solve this, we come to the figure, because we are supposed to compare the force between them. I get the value Fe to Fg is 4.2 into 10 to the power 42. Now, the purpose of doing this question is not only to explain how to use the Coulomb's mathematical expression, but also to show that electrostatic force is about that, the electrostatic force is about 10 to the power 42 times bigger than the gravitational force when you compare two atomic particles, charged particles like two electrons or two protons. So, sometimes we tend to ignore the gravitational force when we compare the electrostatic force. We say electrostatic force is much bigger, so we might even ignore the gravitational force at times. So, therefore, in atomic particles, charged particles, sometimes we tend to ignore it, as I said, because Fe is greater than Fg. Let us talk about the strength of the electric field at a particular point, or which we call as electric field intensity. Now, in gravitational fields, you all learn that in a gravitational field, at different points, the strength of the intensity of the field, referred to as gravitational field intensity, varied. In fact, that is one characteristic of a field. Here also, in an electric field, at different points, the strength of the electric field or the electric field intensity vary based on its position. Now, if we take an example, let's try to understand a couple of points that is associated with it. We say that an electric field intensity is a field that generates, that is produced around any charged particle. And also that if you consider, let me draw it here. So, we have a charged particle here, I will call it Q1. According to that, this charged particle creates an electric field around it. So, if I keep a second charged particle in its vicinity, what happened? We say the second charged particle is kept in the field produced by the first charged particle. And by Coulomb's law, we learned that they are going to experience a mutual force which may be either attractive or either repulsive. So, if I move on to the next point, it says that when two charged particles are kept apart, one particle will be in the field produced by the other, and as a result they experience an attractive or a repulsive force between them. So, according to what I explained here, a very important statement here which says that an electric field can be identified with the help of a charge. If you are using the charge to identify an electric field, we call such a charge a test charge. The one that produces the electric field, we refer to it as a source charge that produces the field. The one that we use to detect a field is referred to as a test charge. If we move on, based on what we learned so far by Coulomb's law, the mathematical expression is that this shows that the two charges are capital Q and simple q. So, let me draw it here, and the capital Q charge produces an electric field around it, and in that field I am keeping the second charge represented by simple q. So, in the field produced by this charge, the second charge, that is the source charge, the test charge is kept. Or else we can argue it the other way. I can say by this charge which produces an electric field around it, then that becomes the source charge. A test charge, this charge is kept in the field of the first one. We can stick to one. So, let me consider this as the source charge, that as the test charge. So, if I look at it in that angle, we say that you can consider Q as the source charge, capital Q as the source charge, and in the field produced by the source charge, the second charge simple q, the test charge, is kept. In the field produced by the source charge, the test charge simple q is kept. We say, according to the equation, it is clear, if you change that, this is affected. If you change that, that is affected, which means both charges contribute to that. But now capital Q is contributing to its electric field. So, when capital Q charge changes, the strength of the electric field changes, and also when the simple Q test charge changes, the force changes, which shows that the force, Coulomb force, depends on two characteristics. One is the strength of the electric field, two is the magnitude of the test charge. Now, we are talking about that, the strength of the electric field produced by this charge. So, I am introducing a particular definition based on the explanation that we did previously. So, according to this, the electric field intensity at a location indicates the force that would act on a unit positive test charge. That means, if I keep a test charge, let the test charge be a unit positive charge, a 1 Coulomb charge. Let the test charge be a 1 Coulomb charge. So, when I keep the test charge, which is a 1 Coulomb charge in this particular space, if it experiences a force, the magnitude of the force gives the magnitude of the electric field intensity. Also says the direction of the electric field is given by the direction of the force exerted on the test positive charge. Magnitude of the force is given by the magnitude of the electric field intensity is given by the magnitude of the force exerted on the unit positive charge, and the direction exerted on the positive charge is the same as the direction of the electric field intensity. So if I move on, according to the definition, the electric field intensity definition is the force exerted per unit charge. So if the force exerted on a charge Q is F, force exerted per unit charge is given by the expression E equals F by Q. And the SI unit therefore will be newtons per coulomb. So if I use this equation to come to the next step, let me explain this way. So on a unit charge, the force exerted, according to the definition, on a unit charge, the force exerted is, its magnitude is equivalent to the magnitude of the electric field intensity at that particular point. So if I instead keep at the same point, I keep a charge Q, on a unit charge, the force exerted is its field. When I keep a charge Q there, the force exerted on it now will be force exerted per unit charge into the test charge I keep there. So we come to the equation F equals EQ. If you now look at what we learned so far in order to further analyze this, by Coulomb's law, we understood the mutual force between two charges kept in a space separate apart from each other. Then we explained saying that one charge is kept in the field of the other, the field produced by the other charge, and by that we came to that definition. The electric field intensity at a particular point in a space can be defined as the electric force exerted per unit test charge. The electric field intensity at a particular point in an electric field can be defined as the electric force exerted per unit test charge kept in that point, particular point. So if you look at them closely, do you see that? I'll further explain it a bit. So I have my charge Q here. The charge Q is producing an electric field around it. In that field, I am keeping my second charge simple Q and by a separation R from it. So do you understand that simple Q is kept in the field produced by the capital Q charge? So if I compare the two equations, try to join them. By that equation, from this equation, let me cross multiply and get simple Q here equals to 1 upon 4 pi epsilon Q upon R squared. I express the same equation bringing simple Q down. So do you understand that that represents the same as that, where the force exerted per unit test charge represents the electric field intensity at that point. At what point? At a point simple r away from the charge capital Q. So the electric field intensity produced by the capital Q charge at a point distance simple r from it is given by that expression. So if you come to the relationship, we get by the capital Q charge at a distance r from it, if you think of a point x here, the electric field intensity produced by the capital Q charge at a distance r at point x here is given by, at point x here, electric field intensity is given by the expression Ex equals 1 upon 4 pi epsilon Q by R squared. Let me explain it one more time. So the electric field intensity at point x at a distance r from the source charge Q is given by the expression E equals 1 upon 4 pi epsilon Q by R squared. Let's discuss about the direction of the electric field intensity. Now, when you have the source charge, we called it capital Q. From it, if I keep my test charge on this side, suppose they are both like charges, for example, they are going to repel each other. So by the source charge, the force exerted on the test charge would be that way. We know that's the force, and according to the definition, that's also the direction of the electric field. So the force's direction and is the same as the field's direction. So if you bring the charge to this side and keep same charge, so the plus charge is going to repel this further. Now in that case, the force is towards that direction, indicates that the electric field is also towards the same direction by the definition. So this shows that the direction of the electric field can be decided by placing a test positive charge at that point. Explanation of the direction of the electric field, we say it's a vector quantity and the direction of the force exerted on the test positive charge gives the direction of the electric field. So if I take an example, I want to find the field produced in the field produced by a positive charge. I want to find the direction, so I am going to take a test positive charge and keep it there. Positive repellent, so the force will be towards that direction. So in that case, we say the positive charge will be repelled. So the direction of the electric field will be towards that. The direction of the electric field will be towards that. If I take a negative charge, for example, that's the source charge producing the electric field. I am testing it by placing a unit positive charge, and the positive charge is attracted. So that gives the direction of the electric field. So that gives the direction of the electric field around a positive charge, and that gives the direction of the electric field around a negative charge. Now, if you try to study the variation of the electric field intensity with the distance. So, graphical representation, E, we know the equation, it's given by E equals 1 upon 4 pi epsilon Q over R squared. So, at a distance R from a charge Q, the strength of the electric field. Now, according to this, how does electric field vary with the distance? Once again, just like the force, E is inversely proportional to R square. Now, if we express it graphically, difference between positive charge and negative charge. So, I have a positive charge, the source charge producing the electric field around it, and that's the test charge I am keeping. So, I am keeping a positive test charge there. I am keeping a positive test charge there. So, this positive will repel the positive. So, the force will be towards that direction, indicates the field is also towards that direction. If I keep the test charge onto the left of it, the positive charge, the positive will repel the positive. So, it indicates the direction of the electric field as well according to the definition. So, we see towards the right, positive side of the scale, E is towards right. So, I have expressed the E in the positive side of the scale, and towards the left of it, E has reversed. So, because the direction has inverted, we have expressed it in the negative side. So, variation is the same as E inversely proportional to R, we understand the pattern. Now, if you think of the negative charge, the two sides switch. Now, I hope you understand, because when it's a negative source charge, you keep a test positive on that side, it's attracted, that and that are the same direction. So, therefore, I have considered that direction electric field as negative. So, when the direction of the electric field is towards left, I have expressed it as a variation to the negative side. And when I keep the test charge on this side, positive gets attracted to that. So, that is the same as that, same direction. So, in that case, if I draw it correspondingly, then I have to draw a positive variation. So, to the positive variation of distance, a negative variation of the field, negative variation of the distance, a positive variation is thus drawn according to if you draw them relatively, if you draw it comparatively. If we come to a question, if we come to a problem, let's read it. When a particle of mass 2 milligram carrying a charge of plus 10 microcoulomb is placed inside an electric field in free space, it continue to remain at rest. Important word there. continue to remain at rest. Determine the direction of the electric field intensity, electric field and intensity of the field at the point it is kept. So, let me draw a force diagram to this. So, I have a particle of mass, there is a weight to it, I have just denoted by symbols, that is a particle carrying a charge. The particle has a weight denoted by mg. Now, they say if only this particle was exerts on it, the particle should move that way down due to gravity. But now the particle continue to remain at rest because this is kept in an electric field, which means that that force is balanced by another force, which must be that. So, that plus 10 microcoulomb charge when kept in an electric field experiences an electrostatic force Fe, which balances the weight. So, if I think of the equilibrium, I get that due to the equilibrium condition of the two forces, Fe upwards and mg downwards must be equal and opposite. So, if I try to substitute to that Fe given by using the previously derived equation, Fe is equivalent to Eq, and that is the weight of the particle. Let me substitute. E is the electric field intensity around this region. We have to find it. Charge, it is a 10 microcoulomb charge. So, we know converting microcoulomb to coulomb, 10 microcoulomb, that into 10 to the power minus 6, that is written in coulomb. So, that is the electrostatic force which is equivalent to the weight of the particle. Weight is 2 milligrams. So, 2 milligrams converted to kilograms, further converted to newtons. So, the electrostatic force is balanced by the gravitational force. When you solve it, you come to a value of 2 newtons per coulomb. Now, how to decide the direction of the force, direction of the field? We know that the fact that is given is that the particle has a weight, but it is being balanced. What is the type of the polarity of the particle, charge of the particle is a positive polarity. So, as we learnt earlier, when a positive charge is kept in an electric field, the direction the force exerts is the same as the direction of the electric field. So, on the positively charged particle, the force exerts upward, which explains that the direction of the field must also be upwards. So, we say the direction of the electric field is upwards and it is 2 newtons per coulomb. Now, a force field is something that we need to visualize. Gravitational fields, of course, we experience in day-to-day life, but electrostatic force fields is something that is hard to visualize. So, in order to make it easy, convenient for us, we use a concept called using field lines or lines of forces. Now, there are a couple of things that we have to know about using lines of forces, or basically a couple of things associated with it. We say that a line of force or a field line can be considered as the path a positive test charge particle will take when it is kept in an electric field. I will repeat, a field line or a line of force can be explained as the path a test positive charge will take when the charge is kept in an electric field. So, when we express a particular electric field by imaginary set of lines expressed as field lines or lines of forces, these things must be understood in order to study the field lines or lines of forces. We say when we represent an electric field using lines of forces, that if you want to identify the direction of the electric field at a particular point, the direction of the electric field at any point in when you express it by lines of field lines or lines of forces will be given by the direction of the line tangent to the field line. So, if you express the lines of forces, you choose a particular point on the lines of forces, draw a tangent at that point, by its direction, the direction of the electric field at that point will be represented. Then again, the magnitude of the field can also be qualitatively expressed by the density of the field lines. Density of the field lines, what's that? We say density of the field lines can be taken as the number of field lines passing through a unit area perpendicular. Imagine there are lines, field lines drawn here. You keep your hand perpendicular to that. Number of field lines passing through a unit perpendicular area, just like a normal definition of density. So, number of field lines passing through a unit perpendicular area can be described as density of field lines. So, if higher number of lines pass through a unit area, that represents a higher density, which represents the magnitude of the field, stronger electric field. A lesser number of field lines pass through represents a lesser field of less intense field. So, the magnitude of the field is therefore less. Then again, the field lines converge to a point charge. If you consider a point charge, for example, let me draw here, you consider a point charge, the field lines that we are going to draw next, will converge around the point charge here. So, if they converge around the point charge, you understand that if they converge around the point charge like this, we understand that the density that we spoke in the previous point, that density of field lines will increase near the point charge, will diminish far from the point charge, because the lines are deviating from each other. That is the next couple of points. They say the field lines converge at the position of a point charge. Therefore, near a point charge, the density becomes very large. So, as it gets close to the point charge, the density becomes very large. Well, we expressed that in a previous result given here. We learned that electric field intensity is inversely proportional to R squared. We saw that when R decreased to a 0, E increased to infinity. That expressed by the same. So, understand that field lines are just used to visualize the concept of an electric field. So, let us look at the rules that we have to follow in order to draw the field lines. So, these are a couple of points that we have to follow as rules when we try to draw field lines or lines of forces around charged bodies. Now, we consider always an electric field line begin on a positive charge and end on a negative charge. Now, that does not necessarily mean a positive charge, existence of a positive charge and the existence of a negative charge is essential to create an electric field. We believe from the positive charge, it is in the concept it is said that it begin at a positive charge and end at a negative charge. Then if you consider a point electric charge, we are supposed to draw the lines symmetrically. We'll come to, when we come to the examples, we'll see how they are drawn. Lines are drawn symmetrically, leaving or entering a charge. And then a very important fact, the number of lines entering or leaving, basically number of lines associated with in the electric field due to a charge depends on, is directly proportional to the magnitude of the charge. For example, you draw a certain number of lines around a charge Q. If you double the charge, you have to double the number of lines that you draw around it. Then we discussed this earlier, density of lines at any point, that is the number of lines passing through a unit line or an area perpendicular to it, is proportional to the field intensity. So, a higher field intensity represents a higher line density, larger number of lines will pass through a unit area. And then we come to another point where if you consider a charge, a point charge, rather a distributed charge, you have plus minus distributed charge over a body. If you consider a large distance from the distributed charge, we can consider comparatively a large distance. So, you have a cluster of charges at a large distance from it. If you want to consider the variation of electric field intensity, what you do, we consider that the distributed charge as a concentric point charge whose charge is equivalent to the net charge of the distribution, and treat it equally. So instead of considering it as a distributed charge, we take it as a concentric point charge equal in magnitude to the net charge and consider the distance in discussing the variation. Last point, important, very important once again, no two field lines can cross each other. This is understood. If you think of a particular point in an electric field, so in this space there is an electric field, you are choosing a particular point in the electric field. The electric field strength, intensity, its magnitude and its direction is already decided. So we can't draw two lines like this indicating, because we can't have two directions, two fields, two directions, two magnitudes. There is only one magnitude, one direction. So two field lines never intersect each other. Is the last point. So we have to use these rules when we draw field lines around charged bodies. So let's come to an example, couple of examples, see whether it's understood. When we talk about isolated point charges, positive, negative. If that's a positive charge, I said path of a test positive charge can be treated as a force line or a field line. So if I keep a test positive charge here, we know that positive will repel it. So this will go right away from it. If I keep it here, right away from it. If I keep it here, this positive will repel it. So yes, if this charge is an isolated charge, the direction, the path of this test charge, positive charge, can be represented in straight lines, and the direction represents the direction of the field, the path represents the force line. So that will be the field lines drawn around a positive isolated charge. That will be the field line, because the test positive charge will be attracted, test positive charge will be attracted. So we say the field lines around a negative charge can be expressed that way. Now if we have more than one charge joined together that we discussed, begin from positive charges, end from negative charges. One more important point here that we discussed earlier. So E is inversely proportional to R squared. See the rule that they mentioned earlier, they said flux density. If you consider an area here, an equal area here, do you understand that more number of flux lines passing through this area, the same area is chosen, but a fewer number of flux lines pass through that, which describes that a higher flux density, a stronger field, lesser flux density, a weaker field, expressed by that. Now, in the presence of different charges, I have drawn here plus Q minus Q. Imagine we have kept a positive test charge. This plus Q will repel it. That minus Q will attract it. We can't have two flux lines. This will pass in a resultant direction. So it will always move. The positive test charge will go from plus to minus. So we'll take that path, the resultant path of the two. If the two charges are equal, you draw a certain n number of lines here. Rule: you have to draw the same number of lines here. The field lines are directly proportional to the charges. And you have to understand it's a three-dimensional impact, even though we draw it on a single 2D plane. And a couple of more examples. And two like charges, plus Q, equal number of lines because the charges are equal. If I draw a test charge here, this plus Q will repel it, and that plus Q will also repel it. So it goes in a resultant path. So you understand, if I look at a particular point here, we have drawn a selected number of lines, there are so many. If I look at this space here, we haven't drawn any lines there. What happened there? If I keep a test charge there, that will repel it and that will also repel it. So suppose at one point these two effects are nullified At that point, the particle, test particle we kept, will not feel a force. That means it is similar to a space where a field does not exist. Such a point is called a null point. So, such null points appear at the two spaces. So, if I further move on to consider two unequal charges, between two unequal charges, look at this, like they are positive charges, but this is Q, the charge here is higher. So, you draw more number of flux lines, minus negative charges, the charge here is stronger, greater. So, you draw more number of flux lines. A null point still appear, because if you keep a test positive charge, that repulsion and that repulsion can nullify each other. But as the charges become unequal, the position of the null point may shift to one side. It shifts towards the weaker charge, the smaller charge, as the two fields, two forces must nullify from each other. So, this is to show the null point existence between two unequal charges. If you further check a couple of more examples to express the field lines of forces. This is the lines of forces acting between two metal plates, carrying opposite charges, positive and negatively charged. You see, unlike the previous example, between the two metal plates, these lines appear to be parallel to each other. But at the edges, the impact has changed. Now, we are introducing something important here. We say between two such metal plates, carrying opposite charges, electric flux lines, unlike the previous one, where in the previous example lines deviated from each other, where the lines appear parallel. If you think of the flux density, we understand flux density at any point. If I keep my hand here, flux density at any point, number of lines passing through unit area at any point is the same. So, we say the flux density at any point is the same. So, we say that such an electric field is referred to as a uniform electric field, where the field intensity does not vary with the distance. So, between two infinitely large plates, we say when they are oppositely charged, a uniform electric field build up. And a few other examples is a positive point charge kept above a metal plate, an uncharged sphere placed between two infinitely large plates oppositely charged. So, the positive charge will induce a negative charge on the surface. So, positive to negative, according to the rules we learned, the field lines are drawn. That is a positively charged plate, negatively charged plate, that is a neutral body. So, positive charges attract negative, negative charges attract positive. According to the rules, positive to negative, field lines are drawn. So, a plus and a minus, as a result, according to the rules in field lines, from positive to negative, the field lines are drawn. Always think there is a test positive charge given, its direction will be, its path will be the field line drawn around it. Lastly, to express the appearance of field lines around metal surfaces in the presence of a charged particle. So, that is my charged particle. These are all metal surfaces of different shapes. So, in the presence of the positive, they are all neutral bodies, but positive attract the negatives, positive attract the negatives, positive attract the negatives, and repel the positives, positives and positives. So, following the rules, we draw the force lines again. So, positive to negative, positive to negative, positive to negative, and we draw the rest of the force lines also. Here, the field lines are introduced to you for you to understand the concept of electric field, to visualize it. So, I will end the lesson for today, competency level 6.1, hoping to meet you at the next competency level with competency level 6.2. Thank you.